Hey everyone, and welcome to this explainer. Today, we're diving into how to add, subtract, and multiply polynomials. We're going to be taking on the role of mathematical architects today. Because, just like a master builder needs to really understand their materials before pouring a foundation, we need to understand the structural pieces of algebra. So we're going to master adding, subtracting, and multiplying polynomials. These are absolutely crucial foundational skills for grade 8 in Algebra 1 that will let you construct and deconstruct some pretty complex mathematical models. Here's our construction plan for today. We'll cover the anatomy of a polynomial, adding and subtracting, our first check, multiplying polynomials, a second check, and finally, a recap with some real-world transfer. All right, Section 1, Anatomy of a Polynomial, our building materials. Okay, before we can actually build anything, we really have to understand the raw materials we're working with, right? I mean, you can't build a house if you don't know the difference between a brick and a pane of glass. So let's get our vocabulary straight. In algebra, terms are essentially the individual bricks of our expression, and they're separated by plus or minus signs. The coefficients are those numbers sitting right in front of the variables. They tell us how many of that specific brick we have or, their size. The degree is the highest exponent in the whole polynomial, which basically acts as our height limit for the structure. And finally, like terms are terms that have the exact same variables raised to the exact same exponents. Think of like terms as matching brick types that can safely be stacked together. Let's look at this anatomy in action with a real blueprint. Take the expression 5x squared minus 3x plus 4. We've got three distinct terms here: 5x squared, negative 3x, and positive 4. And notice how the sign always belongs to the term. Our coefficients, the numbers driving those variables, are 5 and negative 3. That 4 at the end, that's just a constant. And the degree, well, if you look, the highest exponent we see is the 2 on the x squared. So this polynomial has a degree of 2. It's a quadratic. Now listen up, because we are entering our first major danger zone. We can never, ever mash unlike terms together. Seriously, just like we can't magically merge a brick and a window into some weird brick window, we literally cannot merge 2x and 3y into 5xy. The correct move is 2x plus 3x equals 5x. See? They're matching materials. But trying to combine 2x and 3y? Yeah, that's a structural failure. They have to remain separate. Moving on to Section 2, adding and subtracting polynomials by aligning the columns. So, with our materials properly identified and sorted, we can actually start constructing. To keep things perfectly organized, we can build a really strong visual architecture just by stacking our polynomials. Honestly, this is just like the addition you learned way back in elementary school. Step 1, stack the polynomials one right over the other. Step 2, align the columns so that the like terms sit perfectly on top of each other. The x squareds go over the x squareds, the x's over the x's, and the constants over the constants. Then, step 3, just combine the coefficients straight down the column. If you have a totally empty space, just treat it as a 0. It makes the math incredibly clean and easy to follow. But watch your step here, because here comes our second danger zone trap. When you're subtracting a whole polynomial, a super common misconception is just sticking the negative sign on the very first term and completely forgetting the rest. No way! You must distribute that negative sign to every single term in that second polynomial. For example, if you have minus and then in parentheses 2x plus 5, that negative applies to the 2x, making it negative 2x, and it applies to the positive 5, making it negative 5. Remember, you're subtracting the entire group. Let's hit Section 3, check 1, add and subtract. Okay, we've laid out the foundation. Let's pause for a quick check to make sure our blueprint is sound. Look at this problem. The group 3x squared plus 4x minus the group x squared minus 2x. Think about it for a second. What is the very first thing we should do with that subtraction sign in the middle, before we even start aligning our columns? Well, if you said distribute the negative, you hit the nail on the head. We need to change that minus into a plus by flipping the signs inside the second group, so that becomes a negative x squared and a positive 2x. Once we do that, we can stack and add safely. All right, Section 4, multiplying polynomials, expanding the floor plan. Let's expand our floor plan now by learning how to multiply these building blocks together. This is where our structures start taking up some real space. We're going to start simple, multiplying a single term, a monomial, by a polynomial. The absolutely crucial point to remember is that distributing a monomial is just passing that outside value to every single piece on the inside. Step 1, take that outside term. Step 2, multiply it by the first inside term. Step 3, multiply it by the next inside term, and so on. So if you have a 3x on the outside and an x plus 4 on the inside, the 3x multiplies by the x, and then the 3x also multiplies by the 4.
But what happens when we multiply two binomials together? Well, for binomials, we can use this fantastic tool called an area model. It's literally just like finding the total area of a physical rectangular room by multiplying its length times its width. For x plus 3 times x plus 5, we put x and positive 3 across the top and x and positive 5 down the side. Then we just multiply the intersecting rows and columns. So x times x is x squared, 3 times x is 3x, 5 times x is 5x, and 3 times 5 is 15. Finally, we just combine our like terms from the middle, the 3x and the 5x, to get our final expanded floor plan, x squared plus 8x plus 15.
Now, if you prefer working without the grid, no problem at all. We can map this out with purely symbolic steps. And as you'll see, it gives us the exact same 4 partial products we just found in our area model. We just multiply the first terms in each binomial, then the outer terms, then the inner terms, and finally the last terms. First, outer, inner, last. And just like with the area model, step 5 is to combine the like terms in the middle. The math is totally identical. It's just a slightly different way to view the same blueprint.
Moving to section 5, check 2, multiply and verify.
Time for our second quality control check. It is so important to make sure our expanded floor plan is mathematically sound. Let's investigate this setup here. Does x plus 2 times x plus 4 equal x squared plus 8? It's really easy to look at that and accidentally just multiply the first terms to get x squared and the last terms to get 8 and call it a day. But let's act as math detectives for a second. How can we audit our own construction to prove if this shortcut is right or wrong? The absolute best tool in our audit kit is verification by substitution. By plugging a really simple number like x equals 2 into both the start of the problem and our proposed end result, we can prove if our math is actually balanced. Let's try it out. If x is 2, the original problem is 2 plus 2, which is 4, times 2 plus 4, which is 6. 4 times 6 is 24. Okay, now let's check the proposed answer. 2 squared is 4, plus 8 is 12. Does 24 equal 12? Absolutely not. So the audit completely failed. This proves for sure that we missed our middle terms. We totally forgot the outer and inner multiplications.
And finally, section 6, recap and real-world transfer.
Okay, we've built an incredible amount of mathematical infrastructure today. By identifying terms and degrees, aligning our columns for addition and subtraction, and using area models to multiply binomials, you've completely mastered the basics of polynomial arithmetic. But you know, understanding how to manipulate these abstract symbols isn't just some classroom math exercise. It is literally the foundational blueprint for predicting real-world phenomena. Polynomials, specifically the quadratics we've been building today, they map the trajectories of rockets fighting gravity. They model business profit curves to help maximize revenue. They even describe accelerating growth patterns across biology and physics.
You now have the master builder skills to add, subtract, and multiply these expressions with absolute confidence. You know exactly how to align your columns, distribute your negatives, and verify your answers using substitution. So my final question to you is this. If polynomials are the hidden blueprints modeling the physics of our universe, what real-world mystery will you solve with them next? Thanks so much for joining me on this explainer and keep building those math skills.